Now that we understand the importance of data types, let's dive into numeric data types. The ANSI SQL standard defines several numeric data types to handle various kinds of numbers. We can classify them in first integers to represent whole numbers, with each data type differing in its size or capacity, consequently restricting the minimum and maximum number that you can store in different ranges. And second, decimal, to represent fractional or decimal numbers. This subcategory of types can also be subdivided into other two subcategories, fixed point and floating point numbers. Forming the integer subcategory, there are these data types. Integer or int, used to represent whole numbers without fractional parts. And two variations, small int, a smaller range integer, used for conserving some space, and big int, for very large whole numbers. While the standard doesn't dictate the exact byte size, these are typically implemented like so. Small int typically use 2 bytes or 16 bits, ranging from negative 32,768 to positive 32,767. Integer typically use 4 bytes or 32 bits, ranging from negative 2 billion something to positive 2 billion something. Big int typically use 8 bytes or 64 bits. This allows for extremely large numbers, up to 9.2 quintillions on either side of 0. Postgres adheres to SQL standards and follows the size conventions for regular, small, and big integers, but it extends the standard by providing aliases int2, int4, and int8. Serial, small serial, and big serial are Postgres specific variations of respectively int, small int, and big int, and you can also call them by serial 4, serial 2, and serial 8. The difference is, when table calls are of one of these serial types, Postgres also creates a database object called sequence, which handles an integer and automatically computes its next value when you store a new record without expliciting the value for that column. In other simple terms, serials are auto-incremental integers. For numbers with fractional parts, the ANSI SQL standard provides numeric and decimal, or exact decimal numbers. For situations where you need exact decimal representation, Postgres adheres and provides the numeric and decimal type. These are synonyms and can be used interchangeably. The syntax for declaring numeric column is numeric, within brackets you put precision and scale, where precision is the total number of digits, and scale is the number of digits after the decimal point. For instance, numeric or decimal 82 can store or dream 6-figure salary, numbers up to 999,999.99, but not our dream 1 million next project, so please adjust it to numeric 92, or maybe roll it up to numeric 10 too, as you never know. Floating points. I honestly don't like the floating point terminology, and remember my frustration in understanding this concept when I first saw it. I prefer to think of this data type category as the scientific notation numbers. The reason is, it not only uses the same idea of scientific notations that we learn in decimal base in school, but it also mainly used for scientific or engineering tasks. While fixed precision decimal types are trustworthy number representations, they are inefficient to represent huge numbers with tens of zeros or super small numbers also with tens of zeros but to the right of the dot. That's why we use scientific notations, right? For example, the number 128 can also be represented by 1.28 multiplied by 10 to the power of 2, while the number 128 trillions can be condensed as 128 multiplied by 10 to the power of 14. We usually call the 128 the significant or mantissa, and the 2 or the 14 above the 10 are the exponents. Floating points do the same but in binary. While base 10 mantissas can be anything between 1 and 9, because when they are greater than 10, we divide by 10 again and increment the exponent. And when it's smaller than 1, we multiply by 10 and decrement the exponent. Binary, or base 2 mantissas, can only represent numbers between 1 and 2. Floating point imprecisions occur because some decimal fractions cannot be represented exactly in binary. Similarly to fractions like 10 divided by 3, cannot be represented in decimals without infinitely repeating decimals. Let's say you want to represent half in decimal. Okay, 5 is the number that's in the middle of our collection of possible numbers. and always round up to the next digit when added to itself. 5 plus 5 equals to 10, therefore 0.5 plus 0.5 equals to 1. Let's now think in binary. What number do we use when added to itself requires another digit? You have 50% of chances to guess right. Yes, 1. So in binary, 1 plus 1 equals to 1, 0. Therefore, 0.1 plus 0.1 equals to 1. This way we can determine that half, while in decimal is 0.5, in binary is 0.1. So if half of 1 is 0.1, fourth, which is half of 1, is 0.01. Consequently, eighth of 1 is 0.0001, and 0.00001 is the 16th of 1. But what about the 10th of 1? Well, it's a number slightly smaller than the eighth of 1, or 0.001. Or it can be thought as the 16th of 1 plus the 32nd of 1 plus the 6/4 of 1, and this will never end. This is why you might see unexpected results when working with floating point numbers, such as 0.1 plus 0.2 not exactly equal to 0.3 in some calculations. For floating points, the SQL standard defines 3 different data types, all based on the IEEE 754 standard, which is divided into 2 categories, single precision and double precision. The SQL standard defines a third type to float between the 2 IEEE 754 precision sizes. Real is the SQL standard type that typically maps to IEEE 750 single precision standard. Double precision is the SQL standard type that typically maps to the IEEE 754 double precision standard. And float, with an N as a precision, is the SQL standard type that can fluctuate in size, not being restricted to IEEE 750 single or double precision standard. N is the number of binary digits of precision. PostgreSQL implements this type in accordance with the standard, but with specific storage sizes. Real, 4 bytes of storage, providing at least 6 decimal digits of precision. Double precision, 8 bytes of storage, providing at least 15 decimal digits of precision. It's important to note that in PostgreSQL, using float without specifying precision is simply an alias for double precision. Additionally, PostgreSQL provides the aliases float4 for real and float8 for double precision. Postgres also supports special IEEE 754 values, infinity, negative infinity, and auto number. Floating point numbers in PostgreSQL follow the IEEE 754 standard, which represent numbers using 3 components. The first is a sign bit, positive or negative, where 0 is positive and 1 is negative, the same as Miss Lovelace. Second, an exponent, determining the magnitude. And third, the significant or mantissa, representing the actual digits. This representation allows for a wide range of values but can introduce imprecision due to how computers store and manipulate binary fractions. When choosing between fixed precision, numerical decimal, and floating point, real or double precision, consider these guidelines. Use numerical decimal when exact precision is non-negotiable. These types store numbers exactly as specified without rounding errors. Examples you can find are financial applications, banking transactions, accounting systems, and currency calculations require absolute precision, where even a cent of a cent difference can compound into significant discrepancies over millions of transactions. In regulatory compliance, industries with strict reporting requirements like pharmaceuticals, aerospace, where calculations must be reproducible and auditable. World isn't perfect, and these types have performance and storage penalties compared to floating points types, especially for very complex calculations. Floating points, real or double precision, are used when computational efficiency and range are priorities. In scientific computing, these types can represent very large or very small numbers, like for example 1.2 times 10 to the power 38 for real time, which is vital for physics simulations or astronomical calculation. In graphics processing, 3D rendering and image processing might also benefit from prioritizing speed over perfect precision. Machine learning, many algorithms rely on floating point operations optimized at the hardware level. Again, the trade-offs of floating points are well known. These types may introduce small rounding errors, due to their binary representation, making them unsuitable when exact decimal representation is required. But the key distinction isn't about accepting imprecision or not, but rather about matching your data requirements to the appropriate type. So for applications where computational performance and representing number across many orders of magnitudes are priorities, floating point types offer significant advantages despite their inherent limitations in representing certain decimal fractions exactly. Now that we've covered numeric types, let's explore text data types in PostgreSQL. These are essential for storing and manipulating string data in your database. The SQL standard defines the character or char type for fixed-length character strings, where n specifies the exact number of characters to store. In Postgres, when you define a column as char 10, it will always store exactly 10 characters. If you insert a shorter string, Postgres will pad it with spaces to reach the specified length. If you try to insert a longer string, you get an error unless the extra characters are spaces, in which case it will be truncated. While this might seem straightforward, there is an important consideration when using char in PostgreSQL. It implements char with SQL standard compliance, but it's generally not recommended for most use cases. The space padding behavior can lead to unexpected results when comparing values, and it uses more storage than necessary for shorter strings. The SQL standard defines character varying, or varchar, for variable length strings with a maximum length of n. Postgres implements this standard type and adds some flexibility. Varchar n stores strings up to any characters long. If you try to insert a longer string, PostgreSQL will raise an error. Text is a PostgreSQL native string type with no specified length limit. While text isn't part of SQL standard, many database systems support it. Varchar without a length specified. In PostgreSQL, you can omit the length constraint, which makes varchar behave exactly like text, storing strings of any length without restriction. You might be wondering if there are performance differences between these types. Interestingly, in PostgreSQL, there is no performance difference between varchar n and varchar without length specifier in text. They all use the same internal storage mechanism. The only real difference is that varchar n performs a length check on input. When dealing with large text values, Postgres uses a mechanism called toast, the oversized attribute storage technique, to efficiently store and manage them. Let's look at how this works under the hood. When a certain text exceeds a certain size, typically around 2 KB, depending on your configuration, PostgreSQL automatically moves it out of the main table into a special toast storage area. The main table then just contains a pointer to this storage. This approach offers several advantages. It can keep the main table compact for better performance. It also allows efficient storage of large values, and it works automatically without any special handling in your queries. Finally, for truly massive objects over 1 GB, Postgres also provides a separate large object facility, which requires explicit management through a specific API, but offers additional capabilities like streaming access and in-place updates. When it comes to performance, Postgres treats char, varchar, and text types similarly in most operations. However, there are some considerations to keep in mind. Char can be slower due to space padding operations and typically uses more storage than necessary, unless your strings for every new record will contain the exact same number of characters. All text types can be indexed using the same methods, including B3, G, and GIS indexes, depending on your search requirements. For very large text fields, Toast automatically optimizes storage, but operations that need to access the entire value may need to retrieve data from the toast tables, which requires additional I/O. When choosing between char and text, consider use varchar when you have a business rule that limits the length of input. It's the most common one. Use text when you don't need to enforce a specific length constraint. Char is an option if, and only if, either your strings are always of the same size, or the space padding is eventually desirable to your use case. Let's consider a real-world scenario to illustrate these points. Imagine you are building a content management system. Use text for the main content field, as it allows unlimited length. Use varchar for fields with a no maximal length, like titles, for example varchar 100, or summaries, or varchar 500. Let PostgreSQL toast mechanism handle large content automatically.